So this talk is titled XR Graphics in Unity, Delivering Your Best AR and VR Experiences. My name is Dan Miller. I work for Unity Technologies as an XR evangelist. If you guys are interested in some of the content that I'm sharing today, or just general AR, VR, and Unity, I post a lot of my content to Twitter, so you can follow me up there at danmillerdev. So what I want to do today is first talk a little bit about virtual reality, some of the kind of considerations and some of the features that we have for that. Talk about modifying your shader, things like RenderScale and RenderViewportScale, and then finally talk a little bit about the scriptable render pipelines and how they work with virtual reality. After that, I'm going to jump over to augmented reality, talk about things like occlusions, shadows, different rendering techniques, and things to consider. And then finally, I'm going to end with a short demo showing off some different rendering techniques that you can use specifically for mobile augmented reality, but they would also kind of port over to other platforms as well. All right, so first I'm just going to talk a little bit about stereo rendering, the different modes that are enabled within Unity. So we have multipass, which is basically going through the scene view twice, rendering something for each eye. This is the most expensive stereo rendering method, but it's usually the method that we support first because it's the most straightforward for certain displays and technology. Next, we have single pass, which basically takes the two eye textures and combines them into a single kind of double wide texture. And it only goes through the scene graph once, but there is a lot of state changes, so it's a little bit more work on the GPU. And then finally, the most optimal stereo rendering method is something we call single pass instancing, which basically puts both of the eye textures in an array and allows you to save on your GPU and your CPU performance. So single pass instancing is by far the most performant, but it's not necessarily supported on all platforms. If you do ever have issues with rendering in VR for certain platforms or certain scriptable render pipelines or different things like that, as well as just certain effects, I always recommend kind of toggling between these three settings to see if it's related to some of the issues that you're seeing. Now I just want to briefly go over some of the shader changes that you need to make in order to start taking advantage of these stereo rendering methods. And this will basically enable any custom shader that you write to be able to be instanced or in the double wide. So here we just have our normal Vertex shader. And the first thing we need to do is add these macros here at the top into the app data. Followed by that, we add here the output stereo. And then finally, in the actual Vertex pass, we have the instance ID that's going to basically allow it to link in and then initialize the stereo output there. So this is basically the changes that you'll need to make if you're writing any custom shaders. We do have this available on our documentation, so you guys can kind of take pictures now or look that up after the fact. But if you don't do this, then the shader will kind of fall back and will most likely still work, even if you're using one of these different stereo rendering methods, but it's not going to be as optimal and performant as all of the other shaders, which will get automatically adjusted, things like the standard shader in Unity, as you change between your methods. So now I want to talk a little bit about RenderScale versus RenderViewportScale. We've had a lot of confusion along some of the naming. When should you use one? How are they used? What's the best place to use them? And so I have kind of just some small details about this. We've actually renamed RenderScale to Eye Texture Resolution Scale. So this is actually a specific value that you set once and allows you to either up-res or down-res your entire experience. So this is the actual eye texture resolution. As you can see with the rename, it's a little more clear on what it's doing. Some specific use cases for this might be if you're taking a high-end VR experience and porting it to something like the Oculus Quest or a mobile platform. You can actually kind of set the entire experience to be a little bit lower resolution if you need to hit those frame rates and be performant. Coincidentally, if you're porting from something like a mobile platform up to the high end, you can actually up-res your textures. And some of the high-end platforms like Steam VR actually handle some of this in their settings as well, with certain texture resolutions that the user can specify on their device. On the other side, we have the RenderViewportScale. So this value here is meant to be dynamic and adjusted at runtime. So this is something if you were to have a kind of, the valid ranges here I want to point out are only from 0 to 1. So if you want to basically kind of down-res an experience or have it be not at the full scale for some sort of, you have a lot of particle effects or you have a lot of things happening on screen at once, but you want to obviously maintain, the frame rate that's acceptable on your platform, whether that be 90, 120, 72, 80. This render viewport scale can be used to kind of adjust that specifically at runtime. So it's set up to kind of be used in that context. So eye texture resolution scale, you set it once for the entire experience. Render viewport scale can be adjusted at runtime at certain moments or specifications during your experience. So now I want to talk about the high definition render pipeline for virtual reality. This is something we've heard a lot of people are really excited about, and we're excited to see what you guys create. I've worked on a couple projects, kind of porting HDR projects up to virtual reality when the support was first added. So in 2019.1, we added the support, which basically allows you to enable VR. It was only supported with single pass. If you remember from the previous slides, that is the most expensive method. So while it worked, there was still some kind of performance constraints. In 2019.2, we added the single pass instance, so that helps a lot with getting the performance that you need with the high visual fidelity. And here we have kind of a list of things that are not supported for VR. Now, luckily, this was not supported in 2019.1. And so in 2019.2, all of these features are supported, except for the VFX graph. So there's some issues, or there was some issues with stereoscopic rendering in the VFX graph. Those have been solved in 2019.3, and that actually, the fix for that also links into the lightweight and universal render pipeline as well. So if you have tried to use those pipelines and looked at things like the VFX graph, before this fix, it would only ever render in one eye. So if you closed one eye, it looked like it was working. But the good thing here is that in 2019.2, we're basically supporting all of the features. And then in 2019.3, we are saying HDRP is production ready. It's out of preview. And all of the features that are in the high definition render pipeline are supported in VR. Now, there's still going to be some kind of platform and hardware constraints. This is still our high definition, which is on the higher end for what platforms it's supported on. So, you still will need to do kind of optimal techniques for getting your experience to be performant, especially with each of these kind of unique features. So now I want to talk about the universal render pipeline. So we added support for that in 2019.1. A lot of the initial tests that I did with the lightweight render pipeline showed a pretty significant performance upgrade compared to the legacy renderer. So we have certain graphics test projects that we run, and a little over a year ago, I ported one of those to the Oculus Go. As you can see, there are a lot of optimizations. There's certain things like adjusting for shadows, as well as kind of batching things together for reduced draw calls. Unfortunately, with the development of the lightweight render pipeline and the universal render pipeline, there are some limitations right now in virtual reality, especially so on the mobile side. So right now, multi-sample anti-aliasing is not working in VR, in universal and lightweight render pipeline. Post-processing is not supported at all on mobile. And all of these things I just want to point out to kind of inform you guys of the current state. And of course, these are things that were being worked on and we're working to improve and have the full support as the universal render pipeline evolves. So I've been getting a lot of questions about things like fixed foveated rendering, which is kind of a platform or hardware-specific feature for the Oculus Quest and the Oculus Go. That, unfortunately, is also not supported. And Vulkan is something that's being worked on as well. So Vulkan is kind of a responsibility of the core graphics teams, which then the render pipeline graphics teams kind of sit within. So the support for that is being worked on, and then that's going to kind of cascade down into the render pipelines. All right, so just talking about a couple challenges and things like that for the post-processing stack. In general, when using post-processing in both AR and VR, you really have to be careful. Obviously, these platforms are kind of performance critical, so certain things are going to be fairly costly. Certain effects like temporal effects are really just going to add a lot of blurriness. If you think of things like depth of field, some of those don't necessarily make sense in virtual reality, where you don't necessarily want to kind of arbitrarily blur someone's surrounding, especially as they're moving around in the environment. If you do run into issues, as I kind of mentioned earlier, with any sort of post-processing effects, definitely start to kind of switch between the different stereo modes, and that might give you some idea where the issue lies or what might be causing it. And one thing I wanted to mention here with augmented reality, especially on the mobile side, where you're pulling in the camera feed from your device, if you do any sort of post-processing, it's not going to be on your digital content specifically. It's going to be on the entire camera feed. I've worked on some apps and talked to some customers who really want certain parts of their experience to have a lot of bloom and things like that. But the issue is that if you're blooming your experience and then you kind of look up at a light, or even if you're outside or things like that, it is applying bloom to the entire camera feed, not just to your digital content. And this can be good and bad, and I'll show you a bit of a use case here on the demo later. All right, so now let's talk a little bit about augmented reality. So things to keep in mind, this is specific here to the mobile platform. In the out-of-the-box experience for mobile augmented reality, the camera feed gets rendered, and then the digital content gets rendered on top of that. So you can see here with one of my demos here in the park, someone just kind of walks through it, really kind of breaks the illusion a little bit, and you can see there's not any occlusion around the corner of that walkway as well. One thing to keep in mind as well is shadows are not really on by default. In the physical world, almost everything is either casting a shadow or has a shadow on it, and so to me that's something that is really important to kind of really ground objects in augmented reality and start to understand where they are in depth. And then also just kind of keeping in mind that when you're building an augmented reality experience, you're usually obviously testing in your local space, but your users are going to be using it in a variety of different places and locations. The universal render pipeline and the lightweight render pipeline is now supported in the latest versions with AR Foundation 3.0. AR Foundation is our cross-platform library for building both ARKit and ARCore experiences. So you can build them once in Unity, and depending on what platform you deploy to, it's going to use the associated SDK. And that's also now expanding to HoloLens and Magic Leap platforms as well. So there's some different considerations to keep in mind for head-mounted augmented reality. The current platforms right now are an additive display, and what this means is that light is being added to the display, and any basically dark colors or blacks are going to be rendered completely transparent. So if you look at some spheres that I have up here, if you look at the one on the far side there, you can see that basically the bottom half of it is completely transparent. So what you're seeing there is just the normal shading model that you would expect with a light shining down directly on top of it. So it's brightened on the top and then starts to get shaded on the bottom. Now with this, it is more kind of physically accurate, but depending on your content, you're going to get a lot of transparency where you don't necessarily want it. Something that I think Magic Leap did really well in a lot of their samples that they shipped initially with the platform is that they have a shader there, and that's what you're seeing with the other sphere in place, that actually kind of does what I'm describing as reverse lighting. Instead of taking an object and having it go from light to dark, it instead takes the object and keeps the same shading throughout and then brightens the top. And so that's what you're kind of seeing in the sphere over here, and that's how it looks in the Unity editor. It looks a little bit more like that on device specifically. This is an on-device screenshot here, which does not necessarily convey exactly what you're seeing in the headset. But you can see that with that technique, it actually maintains its opaqueness, which is something that I think really kind of contributes to feeling like the content is more in your space. So that's kind of an interesting technique you can use for additive displays. So right now we do have universal render pipeline support for single pass and single pass instance stereo as well on the head-mounted platforms, with the caveat being that the VFX graph does not work yet. So this is something I found recently that I think is also a really good technique. So this is something that I'm calling like negative shadows. And I actually got this from a blog post, which I'll link here in a moment, or reverse shadows. And what it's doing is you can see that this content here is just placed in the space. And from this perspective, it looks like it's on the ground, but there's no real depth cues to understand that. You know, we're in a kind of fixed position looking at the content there in this additive display. So what this individual did is he basically made an outline of where the shadow might be or where the content is, and then feather that content from a more solid white out to kind of full transparency. And so here's what it looks like in Unity. So it's kind of a reverse shadow here that allows it to use the kind of transparent or blacks as transparency to ground the content a lot more. So you can see Andreas there is the one who I found this technique from. And here is the kind of final render there where it is a little bit subtle, but you can see that this is kind of a specific technique that you could use for grounding and adding shadows in an additive display. Some other techniques that I've explored is actually colored shadows, so using different colors besides blacks or grays, since those are just going to render to transparency. And I think for certain content in certain experiences that makes sense. Maybe you're doing like an alien game or something, and you can have purple shadows on all your objects. And the final thing I want to say about additive display shadows is that when content is also casting shadows on itself, it also makes that those parts of the object appear transparent as well. So again, that kind of helps with the physically based rendering part of it, but it does apply some transparency, which can not necessarily be what you want. All right, so now I want to talk a little bit about occlusion. So this bit.ly link here is just a mobile occlusion shader. We originally shipped it with the ARKit plugin. This was our first support for ARKit on mobile devices. And it can be applied to kind of planes or certain meshes found within your environment. So the initial sample we shipped kind of had you scan the ground plane, place some content on it, and then all the other planes that you scanned would actually work as kind of occluders. So if I were to, place a piece of content there, scan the top of this this podium here, and then walk around it, it would be occluded by where the found plane was. I've also seen different techniques for kind of quickly occluding the environment by using things like feature points, which is kind of the basically the small points that the computer vision and ARKit and ARCore pick up before they find planes, and you can apply small little objects to those feature points to act as occluders for your content. The other technique, and the technique that I'm showing off here, is actually the human segmentation feature available in ARKit 3.0. So we have enabled this feature in AR Foundation, which is included in our AR Foundation samples. Unfortunately, the current version of that example, while it enables the feature, it isn't super robust that you can easily take advantage of it in different applications, but that is being worked on. So that sample is going to be updated and allow you to much easier integrate it into existing ARKit apps that support this feature. The next thing is shadows. So this is another just small shadow shader that we also originally shipped with our ARKit plugin. What this shader is doing specifically is actually allowing shadows to be cast on transparent objects. So here I've placed all this content on a transparent plane that has this special shader on it, and then I just have a real-time directional light that is basically creating the accurately shaped shadows that you're seeing here. The one thing to consider in Unity is there are a variety of different ways where shadows are actually being configured and set. You know, they're set on the objects themselves, the light source has shadows, and there's also quality settings. So keep that in mind as you're developing, you know, potentially or on a desktop and then deploying it out to mobile devices. I highly recommend for kind of static objects or anything that you're just placing that's not going to be dynamic to use you know, different techniques like blob shadows. So you can kind of just either create the shape or create kind of a generic circle or something around that object to really kind of help it feel more grounded in the experience. So some other rendering techniques for mobile augmented reality. There are some platform-specific features. So here are two related to ARKit and ARCore. So ARKit has something called environmental probes, and what that'll do is as you scan around the environment, it'll actually understand color data associated with planes and feature points as it finds it. From there, it'll build up a cube map at runtime that you can then apply into a reflection probe and have your physical world be mirrored on your digital content. So that's what we're seeing there. That's a bench by my apartment. I kind of went out, scanned around a little bit, and then placed the content there. And here you can see the bench being reflected on that, I guess what I call like a shiny bean. So that's kind of a cool one. One thing to keep in mind is that the way this feature works is that it is looking for planes and feature points. When I first started building some apps around this feature, I would go outside. I would kind of scan around on the floor. Then I would just arbitrarily scan around in the kind of sky, trying to pick up a lot of blues and things like that. And there's not really any feature points available for the technology to actually get color data from that. It also does use a little bit of machine learning to kind of fill in and smooth out some of the gaps of what it finds. But I have found that this technique works a lot better indoors, where you can actually scan around a little bit more, and it can potentially capture more data. On the opposite side, ARCore has environmental HDR. This actually will adjust the rotation of your directional light, so you can have a real-time directional light that links into this feature and then can match the direction of the shadows that you're seeing in the real world. So this is a really good technique for really making content kind of feel like it's in the real world. It also has ambient spherical harmonics, which you're seeing there in the bottom. That's being disabled and then enabled. And when it becomes enabled, it really matches the environment a lot more, makes it a little more integrated into what you're seeing there. It also does have an HDR cube map for highlights and reflections, which is a little bit similar to what you're seeing on the environmental probe side. So that is available as well. I have found it's not as clear of a reflection sometimes, but in general, I think both of these techniques are better used in a more subtle context. I don't think creating really shiny things like that bean is necessarily the best use case. It can be kind of a subtle technique to just have the objects and the metallic and smoothness fit into the environment a little bit more. All right, so now I'm just going to go ahead and hop into my demo here. All right, so I'll hide all those icons. Let's go right here. So this is just built using AR Foundation. So what I'm going to do is scan the environment. You can see it here on the stage. We found a plane. It actually looks a lot like this carpet. And I'm going ahead and spawn our Adam character in here. Now, obviously, he just has some color data associated with each of his materials. So I have different little buttons down here that's going to start to add up to kind of different techniques you can use for making him feel a lot more integrated in the environment. So the first one here is we have a shadow. So now you can see it feels like he's a little more grounded in the space. Of course, we can kind of get a little closer, further away. We can also assign his kind of textures or material maps. Here we have things like metallic, albedo, obviously, and normal maps, which really help him feel a little bit more integrated. Here we have the environmental probe. Someone pointed out that I misspelled environmental, so I am aware of that. But you can see it's kind of a very subtle technique here that actually is using that scan. And I've only really scanned a small part, but you can see as I toggle that on and off, it really helps him feel a little bit more integrated in the environment. Here we have kind of the default Unity lighting in it, and now we're using that environmental probe to really kind of subtly put him in there. We can also use a technique called light estimation, and what this does is this takes the ambient lighting data from what you're seeing with the camera feed and applies it to the character. So if things get a little bit darker or things get brighter, you can use that to kind of drive the intensity value of your directional lights in the scene as well. And then last but not least, we can have post-processing. So here I've applied some color grading, which kind of puts him in the scene. And again, as I mentioned, it is color grading the entire camera feed, but with that on, it kind of helps make him feel a little more integrated in. So if I toggle all of these off and then all of these back on, you can see the different effects here of how he feels a little bit more integrated into the environment and how these different techniques can kind of be layered together to help him, and help your content feel a little bit more like that. So one thing to keep in mind there is that his shadow is going off the stage. There's not really any logic determining what's preventing that or how that should work. It's just a flat plane underneath him. So that is, again, kind of something to keep in mind about how your users are going to be using this in their environment, which might vary a bit from how you're testing. So I'll just do one more all the way off and all the way back on. All right. So just kind of breaking down exactly what we're seeing there. So of course, we start with the color materials. There we have like the specular, normal, and occlusion maps to apply the correct textures here on Adam. We've also added that shadow there, and again, that shadow is using the specific shader that I mentioned earlier. The way this is just set up in Unity is that the root transform of this Adam object is at his feet. So when I place him on the ground, it feels like his feet is grounded there. And then there's just a plane underneath him that has that shadow shader to get the realistic shape of the shadow on him. From there, we're using the environmental probes, which is that subtle feature. Because I'm developing here on iOS, I'm using the ARKit, so the environmental probes feature, which is specific to that platform. Then we have the light estimation, which just kind of, in this case, dims the lighting a little bit so he's not so blown out, and it's more accurate to the environment. And then finally, the post-processing. And I'm just using the color grading technique here in the post-processing, which allows the same effects to be applied on the camera feed and the digital content, and really helps it feel a little bit more integrated into the environment. And of course, in an example application like this, you would have kind of all of these effects on. The user would only really ever see the camera feed with the color grading or with whatever post-processing you're using. So that kind of helps sell the effect and the idea as well. All right, so that's pretty much it for my talk. if you guys have any questions. I think we have plenty of time for that. I'm also going to be hanging out at the AR and VR booth for the rest of the show. So yeah, thanks a lot. Do we have any questions? It is kind of dark, but maybe. I don't know if there's a microphone or anything. Oh, yep.
You mentioned at the start the RenderScale, and you said that the Vive, for example, at the Vive menu, you have a separate scale. Is it multiplied with another, or does one override the other?
Yeah, so the question was related to the rendering scale, and that certain platforms have that feature enabled as well, like the Steam VR. The question is it multiplied by that, or is it kind of one or the other? My understanding is that you set it in your application, and then Steam VR would kind of multiply on top of that. Yeah.
Hello.
All right.
Hi. My question is, you mentioned that the post-processing is not segmented for the video feed and the 3D things. I'm thinking about motion blur, which would especially be cool in AR without the video feed working. Is there any plan to separate this?
Yeah, so the question is related to post-processing in augmented reality, and if there's any plans to kind of separate the digital content from the camera feed.
Yes.
I don't know if there's any plans specifically in place. That is definitely something that I think is needed, and I know as we kind of develop the platform, it's something that we'll probably be exploring. I know recently Apple, with the ARKit 3 update, actually added some post-processing techniques and things like that. So I think we're kind of exploring if we can link into those, enable some of those for users.
Thank you.
Yep. All right. Yeah, come find me on the show floor if you guys have any more questions. Thanks.